Okay, I wanted to go through number 7. We didn't, I know there's some of you could do this and it makes sense. You're real close to this because we've talked about Q a bunch. But I wanted to show you the work with this. This is where we actually put numbers to it because sometimes we can't see when we're given a scenario like this. By looking at these, we can't really necessarily tell which way this is going to shift. All these are very small concentrations, 0.1 times 10 to the third. Sometimes I like to take this and actually change it into the decimal form because it can be easier to see. 1, 2, 3, 4, and 1, and then this one would be 0.002. Okay, so these are all really small concentrations. So what they're proposing in this is up here we have our equation and we have the K value which came out of our problem here, and we did our K expression. Okay. And so what we have here is a set of concentrations that, notice we have this little 0 here. That 0 stands for naught or initial concentration. So whenever you see these little zeros attached to stuff, that's going to be a concentration at the beginning. So or the concentration before it's allowed to move to equilibrium. So basically what we're saying here is what would happen if we took 0.001 of NH3 and it was in the presence of N2 to 0.00001 and 0.002 of H2. So if I had all three of these things put in a beaker together, what would happen? Would it shift to the left or the right? Now notice these are listed with the product here, and these two are reactants. So in order to do this, all right, we are going to use the reaction quotient, or Q, which we have here. And basically Q is going to plug in these values, initial values, and then we're going to compare it to K, which would be the equilibrium values. All right, so Q is always going to be like in the beginning type value thing. So I'm going to use the same expression, okay, that I would use for K, except I'm going to plug in these hypothetical initial values here, right? Or they could actually be real ones if we were doing this in the lab. So on top here, I still have the product, which is the NH3, okay, 1 times 10 to the minus 3, and I have my N2 followed by my H2, all right? So when I plug and chug this, I get a value of, it's actually 1.25 times 10 to the 7th. That's probably what you got in your calculator if you work this one out. But because this is bound by 2 sig figs, it gets rounded up to 1.3. So what this is telling me this is my current ratio, my starting ratio of product to reactants, I'm getting a Q value, which is higher, actually it's quite a bit higher than K. When Q is bigger than K, this is going to shift to the left. Okay, so it's going to go from the right side to the left side, because what this is saying is that we have way more product, okay, than we typically would be at equilibrium. Okay, so this is going to shift to the left side. Okay, so the larger this value here is, okay, the more we're favoring, more this is on the product side than it is on the reactant side. So whenever we have a Q that is bigger than K, this is going to shift to the left until, okay, these quantities change to match up with the ratio established by K. So here's the first one, okay, that's where we have Q larger than K. We plugged in these initial concentrations to see that. B has another set of initial concentrations, okay, and in this case, our Q is going to equal 6.01 times 10 to the, or times 10 to the second, okay, and so K and Q are equal, so these will be at equilibrium. So if you mix these things together, no reaction will actually happen because the forward and the reverse reaction are happening at the same rate, okay. These concentrations are going to stay right where they're at. All right, and if you didn't guess it, the last one here is where we plug in, okay, these concentrations in the Q, so we're doing a new Q assessment, and this time we see Q as being 2.0 times 10 to the minus third, okay, so this is a little bit smaller than 6.0 times 10 to the minus 2. Sometimes with these you can write them out, it helps a little bit, so this is point K will equal 0.06, where Q in this one is equaling 0.002. Okay, So sometimes I like writing it out like this because initially when you first glance, you're like, well, 6 is bigger than 2. Okay, you have to take into account that this is a negative power of 10. So the 6 is actually 0.06 or 6/100ths, while this is 2/1000. So Q is the smaller value between these two. So we established that Q, okay, our initial concentrations are going to be, it's going to be less than K, and this is going to shift to the right. Okay, so what we see is, and we can kind of see it a little bit here in this 5, because this 5 doesn't have a negative power to it. All right, so it's saying that we have a lot of stuff loaded up here on the reactant side, and it's going to tend to shift over here. Okay, how can you kind of tell by just observing this? Well, here's a little trick. If this was 1, if this was half product, or half a reactant and half product, the ratio would be 1/2, so, or 1/2. So anytime we have something that is much smaller, okay, than that, we know that we're going to have less product over here. Okay, so that's just some ways to look at that. So we're going to use Q to evaluate if the given conditions are going to shift to the left or right, because they're going to shift in a manner to get back to K. All right. Now, here's just a quick little tutorial. We already talked about this. In K in general, when you have a big value for K, that means that we're favoring the product side. When we have a small number for K, that means we are favoring the reactant side. And you can substitute Q in here as well. Whenever we have a Q that is really big, all right, it's probably because we're showing up with a lot of product, okay, on the right side. When K is tiny, all right, we're starting off with lots of reactants. Small Q's, okay, tend to move up, okay, and large Q's tend to move down. All right, and that goes with our shift. So we're going to do some practice with this, but I just wanted to give you the walkthrough because we didn't have time to finish it in class.